Okay. CRM, you want to start?
Yeah. Okay, let me start for some time.
Okay. Then I'll make you an.
Yeah. No, I am already a
I
presenter.
think you are already and yeah. Okay, you can
All
share.
right. Okay, just a second.
Okay, we'll start on the topic of hazards then.
Okay. So I think.
CRM, can you share the screen?
Yes. I'm doing it. Just 1 minute. No, sorry. Okay. Yeah. All right. So we are. We will cover something on hazards. Uh, just a minute. I'm just positioning the screen so that. Yeah. There is something else going on simultaneously. So don't worry too much about that. Cover it as far as possible. Yeah. Okay. Yeah. So we are talking about hazards. So let us just let me just open. Yeah. Let us. Okay. There are some definitions here, which I shall which I shall visit as required. But most important among this is the static 1 hazard and static 0 hazard. All right. So static 1 hazard is when the output momentarily goes to 0 when it should remain 1, and static 0 hazard is when it goes to 1 when it should remain 0. So we have already touched upon these hazards. So let us just look at uh, the realization of some functions and see what can happen. So now we'll first look at function hazards. Okay, we'll first look at function hazards. So look at this. Look at this truth table. Sorry, look at this. You know, the map of the truth table. Okay, and what we are seeing is, so we'll look at various situations. So the same thing. We'll look at various situations. So the first situation we considered. So we are now looking at just to be clear that we are looking at function hazards. Okay, we are looking at function hazards. So in this case, so we're looking at function hazards. Okay. So this is some function that we are considering. This is some function that we are considering, and we are looking at certain transitions. So this is so we are looking at this transition from this min term to this min term. Okay, we are considering the transition from this min term as indicated by this arrow. So basically this is M1 and this is M2. Okay, this is M1 and this is M2. Now the idea of this function hazard, first of all we consider a monotonic transition. So monotonic transition means each input can, so this is a monotonic transition. We consider monotonic transitions. So monotonic transitions, so you have number of input lines. Say, you know, we often call them x0, x1, etc. xn or whatever. All right. Yeah. So by monotonic transition, what do we mean is that, so you know, your input, any combination of the input corresponds to a mean term. So when you are going from mi to mj, okay, on transitioning, from mi to mj, each input bit changes monotonically. Monotonically means either 0 to 1 or 1 to 0. Alright, but not 0, 1, 0 or alright, so not this, either this or this. That's a monotonic transition. So I hope you understand what this monotonic transitions are about. So we consider monotonic transitions because if your transitions are not monotonic, then it is practically meaningless to talk about hazards. Alright. So we talk about monotonic input transitions. So first of all, we just look at something called function hazards. So function hazards are basically, as the name suggests, that these are, I mean the definition is written here, but function hazards are basically independent of implementation. These are more, you know, related to the basic function, the function that you are dealing with. So let us consider some cases. So here you have this M1, you are making a transition from M1 and M2. So your input, say so you have a monotonic transition from here to here, and the function is 0 here, it's also 0 here. So this is fine actually, there is no problem with this. So as it says, there is no function hazard in this case, there is no problem. Alright. So this is a good case or simple case. This is now let us look at this situation. Here, this is M1 and this is M2. Alright, this is M1 and this is M2. Now, just see you have got, so your input, so what is M1? M1 is as shown over here, A bar B, C bar D. So you can change, you can actually come along this path, or you can also come along this path. Okay, this is your transition. Or I don't know, maybe this is color may not be very visible, so let me just try a different color. You can also come along this path. Now, if you look at the red path, there is a problem here. So here you see that this is going from, the function is going from 0 to 1 to 0. So what kind of a hazard is this? Can anyone tell me? So this one is a hazard, okay? So your value should, the function is supposed to be 0. It is 0 at M1, it is 0 at M2. But in between you have this. So this is a static 0 hazard. Right? This is a static 0 hazard. So this is a functional hazard. Now note that this is not dependent on the implementation of this. This is happening because of the nature of the function. Because this is the map of the function. So if your input changes like this, so if it changes along the green path, there is no problem. This is, if you look at the green path is 0 to 0 to 0, so which is fine. But this one is a, this one is a static 0 hazard. Alright, this is a static 0 hazard. So that is a problematic situation. Okay, now let us look at here, so look at this transition as shown over here. So if you look at this, is there any hazard over here? So here what you find is that, whichever route you take, uh,
75, huh? Okay. Generally, okay. Well,
all right, so this is, no matter which way you go, you either have 1 to 0 to 0, or you have 1, 2, 1, 2, 0. So there is no hazard over here. It's you are either changing a little fast or you are changing a little later, but there is no hazard. All right, there is no hazard. Try to analyze this situation now. So this situation is not hard to analyze, because you can see that if you go along this path, so this one is M1, and this one is M2. All right, this one is M2. So here you can see that, if you go along this path, it is problematic. So here in fact you have, it is 1, 2, or let me just put it in red. This one is in fact very problematic. In fact, 1, 2, 0 to 1, 2, 0. All right. So this is a problematic transition. The input, mind you, is changing monotonically. So this one is a problematic transition. You have hazards over here. So this part is a static 1 hazard, and this part is a static 0 hazard. All right. So these are, these are called function hazards, because these are so did I already write that?
Yes, sir.
Yeah, I just want to ask you. Okay.
Share the webcam, please. Sir.
CRM,
Ha.
will you come back after some time?
No, I just want to ask you, is that audible? Whatever is going on, is that audible?
No, not very faintly.
Huh?
Very faintly.
Is the background audible?
Yes, but very low, in a low volume. Or CRM, can I complete? Can you come back?
I think
Okay, you just, I'll come back after some time.
Can you answer the screen a bit?
As you grow, no? Yes. You may kindly pass on if through what is asked about the
Can you
work.
answer the screen a bit?
But the other things, well, okay, just want to convey on it. Yeah.
Yeah, thank you. Okay, so see, CRM is having another Viva. He will come back. Let me quickly cover one small part we did not cover in counter in the last discussion. So we talked about asynchronous counters, where you have a ripple kind of counter where the output of a flip-flop goes as the clock of the next flip-flop, and on the we have seen the logic on the downgoing edge. It triggers. So you have a diagram like this, timing diagram like this. So now let us, but the other thing is that there is a time delay. So the clock, one of the bit of the counter changes, then the next bit changes, and so on. Instead, we can have a synchronous counter where the clock is common. The clock is common for all the counters, and the output of the flip flops, here it's a JK flip flop, the output of the flip flops Q0 to Q3 are the states of the counter, are the state assignments of the counter. So this is a 4-bit counter. We can connect up our J and K inputs by different logic, and what we finally want is a timing diagram something like this. So this is again a mod 4 counter, sorry, a mod 16 counter, but here at every falling edge of the clock, the output Q0 and all these changes. So the frequency is still halved at every as you go down the bit, but you see the changes are only at the down edges of the clock. The advantage is that you have less glitches because everything changes together. You have less glitches. Okay, so let us see how to, and all the different type of counters we talked about, some mod K counter, decade counter, combination of counters, different counting sequences, everything can be done by properly having the appropriate logic at the J and K inputs of the flip-flops. So let us see how to design. And so this is a simple, so let us look at the flip-flops state transition diagram. So you have current state and the next state, and at every up edge of the clock, this is the current state and the next state, and these are the requirements. All these we have studied before for the JK flip-flop. These are the requirements for this. So these are don't cares. These are the requirements. So so if we use this transition function or this activation function, which is for a JK flip-flop, and then we have the requirement or the count sequence given. Let's say I have a 3-bit counter Q0 to Q2, and these are the states 1, 2, 3, 4, 5, and these are the state assignments. So the counting sequence will be just the binary counting sequence, up counting sequence. This is the counting sequence. So it's a mod 5 counter. Even though it could have gone up to mod 8, it's a mod 5 counter, and so it repeats after 100. Okay, so what we'll do, we'll just repeat the same procedure we did for any sequential circuit design to see how, so if this given the activation function of this JK flip-flop and this given the desired counting sequence of the states, how should I wire up the inputs in a synchronous manner? Note that it's synchronous, all the clocks are same for all the 3 flip-flops. Okay, so you do a simple procedure. You just write a transition table, a state transition table. On the left hand side of the state transition table, you write the state sequence and the state assignment sequence. Since here the states assignments are the output of the flip-flops, Q0, Q1, Q2, we just write the Q0, Q1, Q2 sequence that we desire. Okay, and now what we do is that here let us write the requirements of the flip-flop. Okay, so now let us look at like this. Let's look at one of these bits. So let's look at Q2. Okay, let's look at Q2. Note that here what I am having is that, so I'll have 3 logic diagrams each for, anyway, so I have 3 logic diagrams each for Q2, Q1 and Q0. All right, so let's see. So but what we'll do is kind of invert. We don't know what these inputs J0, K0, J1, K1, J2, K2 would be, but we know what the desired values of these Qs should be. So let us look. So if Q2 transitions from 0 to 0, what should be J2, K2? So here you see K2, Q2 is, so this should be, you just consult 0 to 0, Qn is 0, Qn plus 1 is 0 and don't care for J and K. So here Q2 is 0 to 0. So J2 and K2 should be 0 and don't care. Now let us look at the next state. Next state is again 0 to 0 for Q2. I'm just looking at Q2, just forget about Q0, Q1. Just look at Q2, J2, K2, these 3. So again, next state 2 to 3 is 0 to 0. So this should again be J2, K2 should again be 0 and don't care. Similarly, again 0 to 0, 0 and don't care. 0 to 1, 1 and don't care. Just I'm consulting this table. This table I'm consulting. And then 1 to 0 again, which is don't care, and 1. Similarly for Q1, Q1 0 to 0 is J1 0, K1 don't care. 0 to 1, J1 1, K1 don't care, and so on. So I'm following, and so just look at these pairs. So look at Q2, J2, K2, Q1, J1, K1. Look at these pairs, and from this transition table, from the activation function of the JK flip-flop, you write down the requirements on J2, K2, J1, K1, and J0, K0. Once this table is ready, for each of these 6 variables, because you know I have to find the logic to find out J2, K2, J1, K1, J0, K0. These are my desired output that I want. So for each of these variables, as if these are the output of this truth table 1 to 5 and 1, I write down the Carnot map. Okay, and what are the inputs of the Carnot map? Inputs of the Carnot map, you can see, is that there are 3 inputs, Q0, Q2, Q1, and there is, let's say, look at J2. So J2 is the output. So what is the requirement? So now it's just like a truth table. So for 0, 0, 0, it's J2 is 0, 0, 0, 0, J2 is 0. So for 0, 1, 1, for Q0, Q1, Q0, 0, 1, 1, it's 1. And this is a don't care. This is a don't care. Okay. And the other combination of inputs, they are not appearing. So they are also don't care. Other combination of inputs, I have only written down 6 combinations. Other combinations are also don't care. Similarly for K2, look at K2. These 4 are don't cares. These 4 are don't cares. These red ones are the other don't cares which you don't encounter. And there is only 1, 1, which is 1, 0, 0. 1, 0, 0 is 1. So I write down this Carnot map. I minimize this Carnot map, and I get an expression for J2 is Q1 Q0, K2 is 1, J1 is Q0, K1 is Q0, J0 is Q2 bar, K0 is 1. So this we get from this Carnot map. Okay, so then what we do? Just this logic. So this is the expression we got for J0, K0, J1, K1, J2, K2, and so on. This is the logic if we look at this. This logic we just implement. So you remember here we had kept the J2, K2, J1, K1, J0, K0 open. Now we have the logic expression for that. We connect them up. So J and J1, J0, K0 is 1. J1, K1 is Q0, is 1 again. J1 is 1 again. K is K1 is again 1. So J and K are tied. It acts like a toggle. Similarly, J2, K2 is Q0, Q1. Okay, so just this logic. I'm just writing down this logic. This is not for the previous one. This is a different thing. This is a 4 flip-flop counter. Okay, it's a mod 16 counter. Okay, so it's easy. You just follow this procedure. Just make this table, write down the Carnot map, get the logic expression, and wire them up appropriately with some logic gets if necessary. Of course, they will be necessary. You just wire them up. Okay, so any of the previous counters that we talked about, in fact, the same thing you can do. You can also have an up-down counter, as we have discussed before. You can choose a mode of the counter, just like a repel counter, depending on you go up on the rising edge or the falling edge, because rising edge can be you see that if you use a JK flip-flop, if the falling edge is a up counter, okay, if you use a T flip-flop, if the falling edge is up counter, the rising edge will give a down counter. So same thing here, similar thing here. You just have a mode line and you can use the same thing. So this is the circuit. In fact, this is the same circuit that we used for a dual mode repel counter. The logic is the same, similar logic holds, but only thing they are synchronous. All the clocks are tied. And so any other counter, a decade counter or any mod K counter, So you can just design in the similar manner. You can just draw the transition table, and the activation function of a flip-flop ties Q2 to J2, K2, Q1 to J1, K1. So according to the activation function of these transitions that you need, you write down J1, K1, J2, K2. That's the requirement. And then you form individual kernel maps involving each of these variables as output and Q2, Q1, Q0 as input. Get the thing? Wire them up accordingly. Okay. So this is the structure. This is the structure. You can have both an up-down counter, which if you just activate the up counter, this is the effective circuit. This will look like this. This will be turned off. This is the effective circuit. It will act like up counter. Similarly, this will be the effective circuit when the down bar is 0. Okay. So this will be the effective circuit. These circuits will turn off. This will be the effective circuits. Okay, so these counters are very important for many in many applications where you have to count something. Even in CPUs, there is always a counter, which takes us into account many things. So these counters, along with registers, shift registers, we have studied all forms of shift registers, like you have studied all terms of shift registers where we can have serial in, serial out, parallel in, serial out, and such things. So shift registers as counter, they form an important part of many circuits. All right. So let's see if CRM is back. So I am done with my thing about counters. I don't know if CRM is back. No, CRM is not back, so we can continue. All right. Okay, so shift register, as you all know, is nothing but a bit array. Okay, so you can think of this as just let me share once again. Yes. So see, what does a shift register does is that you have a bit array. So this is a 4-bit array, and you can have, and these are kind of the input bits. So let's call them as x1, x2, x4, or x3, x2, x1, x0. Similarly, you can have either parallel output y3, y2, y1, and y0. You can either have a serial output or serial in, and then there is a control sometime, and there may be control output. So see, these are kind of arrays. Arrays in the sense that these are an vector of bits. Now they can either be written parallelly, that means all 4 bits can be written together, or they can be written serially. Similarly, they can either be read parallelly, that means all 4 bits are output together, or read serially, that means 1 bit at a time can be read. So depending on how you do this, you have either a serial in, serial out, parallel in, serial out, serial in, parallel out, and parallel in, parallel out. You can have this 4 configuration. Then what basically happens is that you can see if it is it basically shifts. So initially, if it is 0, 0, 0, 0, and you are trying to write 1 will come here. These zeros will be there, and then you try to write 1. This 1 will shift here, and this 1 will come here, and so on. So it shifts. That's why it's called a shift register. So now these are extremely useful circuit elements because they can be used as memory elements. They can be used as memory elements, and since this is an array, you can store a word of memory here. and this individual setting they can work out in different situations. For example, it's a serial in parallel out, say you are typing something in the keyboard. So what happens is that often from the keyboards one key at a time, one key input at a time goes and stored in a register called a buffer, and then when the computer reads, it reads whatever the entire word that is stored, it reads at a time. Okay, so or sometimes say that you are communicating through a network. The network is a serial network, so it transfers only one bit at a time. So the computer writes in the buffer x0 to x3, and then it transmits output one bit at a time. So it's parallel in serial out. In general, it can be parallel in and these circuits I think you have already seen before. You have done in the lab. I'm not going into detail of them. So what I would like to say, in your computer you will have memories or registers as several of these kind of shift registers, one word at a time. Okay, and then this 4 vector denoted by a sign sometimes like this, these 4 lines which can either write to the memory. So you basically have a structure like this. You have a set of registers R1, R2, R3, R4 like this, and these are the input lines that are coming with which you can write to each of these registers, and then the outputs also you can write, and then you can control that which register will be read, which of this register. You have a set of control thing. So this vector of bits are called a bus. So for example, here you are writing the data input output. It's called a data bus. Okay, and here you are choosing which register to which register. So just you are choosing which register to. This you call a address bus. Okay, sometimes these two are shared. The data and address bus are shared sometimes. Similarly, so you can have a control bus, you can have a instruction bus, and so on. So these are shared. Okay, so this is a very common structure in a computer where you have a I should say battery of a collection of these registers and with a common data bus and an address bus. Okay, so let us see. So see what does this? Okay, there is another way to think about this. So this is kind of like a multiplexer. When you have the parallel in, serial out, it's like a multiplexer. So let's say you have x0, x1, x2, x3, 2 in control lines. If you are doing a serial out, so depending on the value of control line, either you can make this as out, or you can make this as out, or you can make this as out, or you can make this out. So you are choosing which of these bits you will output. It's like a multiplexer. So this can also be thought of as a multiplexer. In a programming equivalence, you can just think of this as an array, and this multiplexer is picking up the ith element of the array. All right. So now, see, so again we can have two type of shifting. One is called a logical shift. So if we have 0, 0, 0, 1, and you have a left shift by 1 position, or rather, let's say right shift by 1 position, or you will have, let's say write it like this, you have leading zeros coming in. Okay, you have another right shift, you have 0, 0, 1, 0 coming. Or you can have an arithmetic shift where it rolls around. So you can have, if this shifts, you can have 1, 1, 1, 0, 0, this rolls around, then you can have 1, 0, 1, 0, this rolls around, and so on. Oh, no, I think this doesn't roll around. The leading bit Yeah, okay. So you can, and then you know that this is equivalent to divide by 2 for the left, divide or multiply by 2, depending on which way you shift. Now, usually we have told these registers are a collection of flip-flops, but sometimes this kind of rotate and shift operation, they can be very easily implemented without a sequential circuit by just using combinational circuits. Combinational circuits just using multiplexers. The advantage is that usually the delays of this circuit will be much less than the delay of the sequential circuits. Okay, so many of the processors like these ARM processors and other, they have something inside their CPU which just uses these combinational circuits to implement these shift registers, both in the shift and rotate mode. All right, I'm not talking. So this is how you do the serial in parallel out. So just look at this a little bit. You can choose which input. You have a multiplexer. You have a common clock. No, not a common clock. You can easily see if you just look at the logic. You see this is the output and these are the inputs. Okay, and these are the inputs. Now this depending on what the D values are be, D values can either be the first input or if there is no shift, or the second. So it decides how many shift will be there, or the second input. In this case, the multiplexer is chosen in that way. So note that this is a vector. So there are two controls in this multiplexer. It can be chosen in this way. So depending on how you shift leading 0 or whatever way you shift, you can choose which of these input lines. So there are 4 input lines. Which of the, because see, every shift is just a movement here or a leading 0 coming in here. Okay, so accordingly, so this can be obtained by the previous input. So accordingly, you add up this thing and you ask the multiplexer to forward the corresponding element. Okay, and then the D flip-flop, as you know, we'll just transfer it in the next cycle. You can do it. So these are the codes. So if this is 0 0, this is 0 0. Basically, nothing will happen because if 0 0, this first line will be chosen. The first line will be chosen. The first line is same as current output. So similarly, here the first line is same as the current output. So 0 0, basically there will be no change in the output. So it's no up. Let's look at 0 0 1. So if it's 0 1, the next line will be chosen. The next input will be chosen. Okay, the next input will be chosen. Let's look at what's the next input. So here in this case, the next input is this one. D4 is the next input for D3 is the next input for D0. So this will come here. Here it will shift it. So this output. Let's look at the second input here. Yeah, this is out 0. So out 0 will be in 1 for the left shift. And similarly, out 1 will be in 2 for the second input and so on. Now let us look at the right shift. In the right shift, what happens is that it will be the other way around. So it's 1 0. So the third line will be chosen. Third line will be chosen. You look at the wiring connection. In the third line, there will be a right shift. Okay. Finally, 1 1 is load. 1 1 is load means now the input will be chosen. So whatever is the input will be written to the output. Okay. So depending on this combination of the multiplexer inputs, you can have either a left shift or the right shift or no shift shift register. And this is parallel in, parallel out, parallel input output. Okay, so we will see that we can actually realize this entire shift register operation even without this flip-flop by just using multiplexer. Okay, so the idea is like this. Idea is like this. See, if this is my input and this is my output, so when I'm shifting it, it basically means I'm short circuiting. Let's say two things. I'm just short circuiting this. I'm using a multiplexer. I'm just making the second input as the third output and so on. I'm just shifting them. All right. So, so if you know if there is a fixed amount of shift you want to do, you can easily do it in the multiplexer. So that's what exactly has been done here. That's what exactly has been done here. Okay, you can just one shift you can do. Similarly, it's easy to do a two shift. So this entire circuit, I could have made a slightly different rewiring. So you see this is connected here, this is connected here. I could have slightly rewired to make this a 2-bit shift. So this is a 1-bit shift. I could have easily made it a 2-position shift. Okay, I can easily make up this. Similarly, I can easily make a 4-position shift. I could have easily made a 4-position shift. So if the now depending on how much shift you have to do, I'm not talking about 3 and 1. Sorry, I'm not talking about 3 and 5-bit shifts and so on. I will see how you can do that. So what we can do is that now if you are asked to do X amount of shift and if X matches with any of this, you can so you get what I'm trying to say. I'm trying to say this is a 1-bit shift register. Similarly, I could have made a 2-bit shift register. I could have made a 4-bit shift register and so on. I could have also made a 5-bit or a 3-bit shift register. I'm not making them. I'm just making 2-bit, 4-bit and so on by appropriately connecting up the multiplexers. Okay, this is an example I've given, but you can easily do this for the other shifts also. And then depending on if it is a k bit, which k matches which of this, I could have chosen the according multiplexer. Now the problem is if this k is variable, then how do I do? Let's see I want to do a 5-bit shift. So I can actually do it by combining this 4-bit and 1-bit shift, because see they are compositional. So if I first shift by 4 bits, then I shift by 1 bit, I get a 5-bit shift. So I can somehow first do this shift, then do this shift, I get 5-bit shift. Now, so what I do is that I have another kind of multiplexer circuit here, which takes as input the binary representation of k. Let's say the binary representation of k is this. So this is a k-bit shift that I want. If this is the binary representation, which is a 5-bit shift, this means that you make a, and I have all this. I have a 1-bit shift, I have a 2-bit shift, I have a 4-bit shift, and I have a 8-bit shift. All these possible. So this is my 1-bit, this is my 2-bit, this is my 4-bit. I also have a 8-bit shift. So what I do, this means is that I first shift through the first. I make the data go through this first. I ignore this because this is 0. Then I pick up the 4 bits. Then I shift it to this. I choose this circuit. Then I ignore the 8-bit circuit. Okay, so I ignore this. I choose this. I choose this, and I ignore the next. This will give me a 5-bit. So if I can build this multiplexer circuit, which will basically let me choose this each of these 2 to the power n bit shifters, then I can get arbitrary number of shifts. So this is implemented something called a barrel shift register, barrel shift rotate register. So this is my 1-bit register. This is my 1-bit shift register that we have drawn here. This is a 4-bit one. This is a 8-bit one. This is my 1-bit shift register. This is my 2-bit shift register. The same circuit. This circuit, but you note that with a different wiring diagram, depending on how much shift we want to do. Different wiring diagram depending. This is a 4-bit shift register. Okay. And now these lines determine whether I will take this or not take this. Okay, by the way, there is this has additional small amount of circuit for rotate. This is just for shift. This is a 4-bit rotate, so this will be pulled in. This is a 2-bit rotate. It's a 1-bit rotate. Okay, so depending on this is my control line. So B0, B1, B2. So if I have a k-bit shift, I'll just choose this accordingly. Let's say this is the value. So I'll choose this shift, and not this shift. I'll activate these lines. Okay, and this input will come in as this k, binary representation of k will come in the input. It will activate this and it will make the output. So these inputs will accordingly get shifted or rotated, and you will get the output. And this is extremely fast because this entire thing is a combinational circuit. Maybe we'll look into more of this. I have just quickly skipped all this logic, but actually, if you look, you can also get it. But maybe we'll go into more details of this, and you have this. So this is very popular. This is extremely fast. This is used in ARM processors. So all these Apple iPads and all this, they use the ARM processor to do all these things. Okay, I think we are done. Okay, I think let us stop. So we are meeting at 2 o'clock for the very log. So CRM, we are leaving. Okay, all right. Thank you.